Hi everyone. So last time we started to talk about finite free probability, and our first step was to actually define a finite additive free convolution, which was defined differently. It was defined using like it was motivated. The definition was motivated by this most important exercise that told us that if A and B are free, if A and B are any two elements in the algebra, you can free them by taking a third element, which is a Haar unitary element, and conjugate B, therefore making this conjugated version of B free from A. So that motivated the definition of, a freeness-free definition of the additive finite free convolution by any finite dimensional operator A and B conjugating using a Haar unitary, finite dimensional Haar unitary that exists, right? A Haar unitary matrix or operator, and kind of define the additive free convolution, finite free convolution, to be the expected characteristic polynomial of the sum of A and the conjugated B. So we had the definition in place. We're going to talk more about it in future units, but we don't want just the definition, but also a theorem. So the theorem that we had in free probability was essentially the R theorem, let's call it, which tells us that the R transform, which is a version of the cumulant generating functions, is very simple with respect to the addition of sum of three random variables, namely the R transform of A plus B is the R transform of A plus the R transform of B. So we had this diagram, right? You start with the measure and you go to the Cauchy transform, then to the K transform, and then easily to the R transform. And on that level, it's very simple what's going on. When you add random variables, you just add the corresponding R transforms and then you go back. So in finite free probability, we are not going to have such a clean definition or clean theorem, but we are going to have in some sense, a kind of a better theorem. What we are going to show is a bound on the R transform. So it's not going to be the case that the R transform of A plus B, a plus in the sense of the free additive convolution, is equals to the sum of the R transform, but it's going to be bounded pointwise by the corresponding R transforms, which is enough for our needs because in finite free probability, we are only going to care about the support, and that will be enough for us for our needs. So you won't get the precise measure, but you get some bound from which, on the R transform, from which you can, as we will see, you can get as a corollary a bound on the support, at least one-sided support of the measure. Okay, so the proof of the finite R transform theorem, let's call it like that, is not simple. It actually doesn't at all follow the proof of the R transform from free probability, which used heavily the fact that cumulants, I mean, it was a one-liner from the fact that cumulants of three random variables, so the cumulant corresponding to A plus B is just the cumulant of A plus cumulant of B when A and B are free. But that was kind of, it built on a lot of things that we did, in particular the Mobius inversion formula and all of the lattice stuff that we did and so forth. So it required a lot of work. And proving the R transform theorem for finite free probability, that version, so you can like it or not, but it has nothing to do with the proof that we had for the free, like infinite free probability theory. So we'll have to do things from scratch, even though it's the same definition, you might expect something that is kind of a reduction to actual free probability rather than doing everything from scratch. And the whole technicality issues are going to be around polynomials, because now that the support size is finite, polynomials will be a nice way to encode the measure, right? So if you have the lambda 1 up to lambda d as your eigenvalues, or put differently, the discrete measure that you care about is supported on lambda 1 up to lambda d. then you can just encode it either using the Cauchy transform, and we will, but also as the roots of a polynomial. And there is a relation between that, and we saw that, and I'll remind you of that now as well. So the proof of the R transform is going to be based on like working with polynomials. In particular, since we are going to talk about self-adjoint operators, these are going to be real-rooted polynomials. And it turns out that there is a lot of theory about real-rooted polynomials, more than you might expect. Might have expected, and I think the historical reasons for that, I'm not sure about that. That's what I kind of gathered from different papers, is that it was a real attempt at trying to tackle the Riemann hypothesis, because you know, you want to prove all the roots are on the, you know, plus half like real axis in the complex plane, so you can just flip it a little bit and try to figure out what kind of structure you have from polynomials, or maybe not just polynomials. All of those roots are all of its roots are on a line, right? So it's going to be there is a surprising amount of known theory about that, and from the 20s and 30s from last century, and it's going to take a while. So my plan is to first start with some preliminaries, state the theorem, and then the proof is going to be based on like 5 more or less components. Some of them are more insightful, some of them are, you know, quite technical. It's a matter of taste also, but that's, I think, generally should be generally acceptable as a statement. And so I will postpone the proof, for example, of what's called the pinching lemma to another video, so that you won't affect the kind of the flow of the proof. Okay, so with that, let's start and recap what we did last time. Okay. Okay, so as I remember, last time we talked about the additive finite free convolution, and we motivated it using, as I said before, the most important exercise and so forth. And we defined the additive free convolution with some parameter d. So that's what you see here. As this expected characteristic polynomial that you have here. Okay, and here you see we use the Haar measure in part of the definition, and you remember there are there are many Haar measures, but there are 2 Haar measures that are important for us: the unitary and the orthogonal, corresponding to the complex and real valued spaces that you care to work over. We are going to work over the real, so we are going to consider the orthogonal version, but it's all the same. Okay, so it's that unique distribution which is invariant under left and right multiplication. Okay. Okay, and the last thing we did, if I remember correctly, was to actually prove the part of the definition which is a theorem, namely that this definition is not ill-defined, it's well-defined. Namely, it is indeed the case that this expectation depends only on the spectrum of A and the spectrum of D, rather than on the eigenvector structure. Right? So in a sense, what we are kind of saying is that, and that's a bit of philosophizing here, is that freeness, when you consider finite dimensional operators, is about the underlying eigenvector structure. Right? So the distribution is of the eigenvalues, but freeness, which is an abstract notion, if you want to give it some interpretation, then for matrices, finite operators, also for infinite operators, but for finite operators also, it doesn't exist as we saw. It's a phenomena of infinite dimensional operators, but whatever you the thing that you should think about when you think about freeness working with finite dimensional matrices or operators is that it's about it's not about the eigenvalues, it's about the way that they are kind of rotated or reflected in space. Okay. Okay. Yeah, actually, I think we also did that. So, right, so we defined the Cauchy transform of a polynomial, which was actually the same definition as we had before, namely the Cauchy transform of a polynomial, just a nice way of saying that, instead of saying so we can consider the measure, which is this kind of Dirac convex combination of Dirac measures, where you put your atoms on the corresponding eigenvalues or roots of the polynomial. So instead of doing that, we're just saying that the Cauchy transform of a polynomial is this thing, which coincides with the Cauchy transform of the measure, which is supported on the roots of the polynomials, taking multiplicity into considerations. And there is a nice little formula that you can easily prove, which relates the Cauchy transform to the polynomial itself. Okay, and it's an easy kind of calculation that you can show, that you can prove. Namely, the Cauchy transform is a normalized version of the derivative over the actual polynomial. And as I said, in free probability theory, we consider this a function, the Cauchy transform, as a function from the upper half plane to the complex plane, and it actually happened to have image which is the lower half plane. But in the finite free probability, we are going to only consider it as a real valued function, in particular only to the right of the leftmost root, max root of the polynomial, or lambda 1. And this was the example, and that's the picture you should have in mind when you consider Cauchy transforms. So that's a kind of a standard Cauchy transform, a typical one. And you see that every root of the polynomial translates to a pole, like obviously, because you have a pole here. All poles are simple, and the behavior is always like that. You have these, the rightmost branch looks like more or less 1 over x, maybe normalized, and then you have all of these other branches, and then there is the leftmost one, which you don't really care about. You also don't really care about any of those. As you will see, we care only about this one. And so the last thing we did was to say that if you are looking at a real rooted polynomial, and let's assume it's has a positive leading coefficient, that would be simpler. You can almost always assume it's also monic, but not always. So we care about the roots, right? So we don't really care about that. But if you have a real rooted polynomial which has a positive leading coefficient, then the rightmost branch, namely if you restrict P to what happens to the to the right of lambda 1, which in our case it's in this thing, right? Then as you can see here, the image of that is the open interval from 0 to infinity, right? Because you start from a pole from infinity, or you go all the way down to 0 because of the positive leading coefficient. Otherwise, it would have been a mirror with respect to the x-axis. So let's consider only positive leading coefficients. And not only that, it's strictly monotone decreasing. In particular, it's invertible, right? Because of that. So what I'm saying is that, and that's the last thing we did, is that you can define an inverse to, well, not P, but to P restricted to that open interval. And the inverse of that is really the max inverse of the original Cauchy transform, right? Because you'll get the largest image. If you set your W at some, say this W, which was supposed to be 2, then you get several free, in this case, like the degree, pre-images, but the largest one will correspond to that branch that we're looking at. So that's the max inverse. You can think of it as the max inverse of the Cauchy transform. And that's called that. I mean, we will call this the K transform, and as we'll talk about next, this is indeed the K transform that we talked about in free probability, which was induced from the Cauchy transform. Okay, but 2 remarks that we will need is that, I mean, we are going to use the K transform in a different way than we used it in free probability. We are going to use the fact that it always abounds on the max root of P, right? So for any W you'll take, it's always a bound. You can see it here. For any W that I will choose, I'll get a value, and it's always larger than, in this case, 2, which is the max root of P. You can see it here. And as W goes to infinity, right, you get closer and closer to this last pole, which is 2. So the limit as W goes to infinity of the max inverse or the K transform is exactly the max root. Okay, so I think that was the recap. We had this example last time, which I just kind of did now on the previous sheet. And okay, so let's move on. So as a remark, the K-transform of free probability theory was actually defined to be, I mean, just to connect the two things, it's the same function. So it was defined differently, or it was like a priori it looks different. It was defined to be the inverse as a formal power series of G of Z, right, of the Cauchy transform. Right, we took the Cauchy transform and then we inverted it. And if you remember, sometimes when you inverted it, you got more solutions, right? You got maybe you got a quadratic equation, and then you got two solutions, and then we chose in the examples that we saw, we chose the plus or minus in this case of, before the square root of the discriminant, we chose it so that we'll get to the right solution. And the right solution was usually coming from the fact that we knew something about the Cauchy transform, for example, that it looks like 1 over z as z goes to infinity, or in terms of k, or the k transform, we know that the k transform starts with 1 over z. So we picked the inverse to be the inverse, for example, for the k transform that looks like that, right? And here as well, that's also what's going on, right? Because you have several, so the k transforms that we define in finite probability is the max inverse. And if you think about it, let's go to this example here. There are several inverses. You can pick several branches. You can invert the function. You can invert the function, the G function, in any domain which is 1 to 1. So for example, after the last pole, it's 1 to 1, and that's how we chose the inverse. We took the max inverse, but you could have also defined it to come from this part, right? To invert it according to that. And what I'm trying to say is that taking the max inverse and picking up, so that's finite probability, and picking up the K transform, which looked like 1 over z plus stuff, which was free probability, is the same thing. Because indeed, this is the unique branch that looks like a 1 over z, or 1 over x in this case, as z goes to infinity, right? Because if you add the Cauchy transform and you're far away, then all of these things look like 1 over x, so you get free of these 1 over x's over 3, so you get the 1 over x. So choosing the max root is precisely the same thing as choosing the that inverse that looks like 1 over z plus something. Just a remark, we won't really need it, but I do want to connect what we did in free probability and finite free probability, so I thought it's worth saying that and get our head around it. Another thing, now it's actually a different way. It's something that's different in free probability and finite free probability, is that in free probability we used the K transform to compute the actual measure, but on the way the K transform of say the sum of D or whatever copies of mu, or the sum of any any measures corresponding to three random variables. So for example, what we started with the measure, we did the Cauchy transform, we inverted it to get the K transform, and then from the K transform we move to the R transform. That's very simple, you just subtract 1 over z. Here everything is simple on the level of the R transform. So for example, if you want to compute the additive convolution of mu with itself d times, which we call mu d, so you just multiply d as the transform d times, and then you can go back to the K transform of mu d by just adding 1 over z. You can, of course, also short circuit it by just multiplying this by d and subtracting d minus I times z, same thing. And from here, we usually went back to the G transform of mu d, and then using the Stieltjes inversion formula to mu d to get the entire measure, all the information. In free probability theory, we are not going to do that. I mean, we are going to do the initial stuff. For mu, we are going to compute the Cauchy transform, the K transform. That's difficult. That's inversion. Okay. And then we are going to do this step, which is easy. But from this K transform, we are not going to get back the Cauchy transform of the measure, because the theorem that we are going to prove anyhow doesn't give us enough information to infer things about the entire measure. We're only going to get a bound, not an equality between the corresponding R transforms. But nonetheless, as we'll see, and actually we'll already started to say parts of what we will need, the K transform is going to give us a way of bounding the support from the right or from the left, which will be enough for us. And nicely enough, we won't have to invert the second time. So we do invert from on the left column from G mu to get the Cauchy transform corresponding to mu. But once we have the Cauchy transform corresponding to mu, we can easily compute the Cauchy transform of MD. And that's all the inversion you'll do. From here, it's going to be we are going to bound the support in a different way. Okay, and we're essentially going to use this. The fact that the Cauchy transform for every W gives you a bound on the max transform of the polynomial, which is the max root of that is going to be related, of course, to the largest eigenvalue of MUD or whatever. Okay. I mean, it's fair, right? You ask for less information, you don't get the entire measure because you don't have such a strong R theorem statement. You only get a bound on the support, so it kind of makes sense that you would have to computationally work a bit, to work less a little bit. Okay. So I want to reinterpret this Cauchy transform, the K transform one more time. As I told you, the whole thing is going to be about polynomials, okay? So it doesn't look like it, but the K transform in a sense is highly related to polynomials. I mean, it looks like a max inverse of this Cauchy transform. It doesn't look like a polynomial, but it is, I mean, in some sense. So what I'm saying is, if you fix P, of course, you're going to fix P, but also fix W, namely the point you want to max invert, like the horizontal line that you want to ask, what's the rightmost point that meets the Cauchy transform. Then it turns out that you can express this as the maximum root of some other real-rooted polynomial. Okay? So let's see why. Okay? So it's a very simple calculation, but I think it's a kind of a brilliant move. So the Cauchy transform is this thing, right? I mean, that's the formula that we have for it. It's the normalized version of the derivative over the polynomial itself. And forget about max root, or max solution. But if you ask, what is an X that satisfies this equality, right? W is now given. Then because of this equation, moving things a little bit to the sides, you see that any solution to that equation, a solution to that equation, X solves, it's an if and only if statement, this equality, but now you have a polynomial here, right? So if X solves that, and that's an if and only if, then it also holds that P of X minus this 1 over WD times the derivative at X is 0. Right? A more fancy way of saying that is that, because we are going to use it a lot, is that we can define this operator on polynomials. We are going to use it only on real-rooted polynomials, but generally on polynomials. So this operator U sub alpha is, it's a polynomial, and what it spits out is the polynomial minus alpha times the derivative of that polynomial with respect to X. It's only going to be univariate all the way. So, right, so capital D is also an operator. It's a linear operator. It's a differentiation operator with respect to X. And so using this notation, using this operator, which you can also write in a fancy way like that. So U alpha is 1 in the sense of the identity operator that takes a polynomial and spits out that polynomial, minus alpha D, namely that's the minus in operator world, right? You subtract the operators. And the alpha D operator is just what you'd think it is. You multiply by alpha and you differentiate. It's a linear operator all the way because the 1, the minus, the alpha, and the differentiation with respect to x are linear. So using this notation, you can say that x solves this equality, and again, w is given, if and only if this polynomial, right? So you apply the u operator with alpha, which is 1 over wd, apply it to p, you get a polynomial. That polynomial evaluated at x is 0. So saying that x solves Cauchy of x equals w is the same, which is non-polynomial, is the same as saying, again, w is kind of built into the circuit or to this polynomial, says that there is some operator that when you apply to the polynomial, then those x's that are roots of this polynomial are exactly the x's that satisfies the Cauchy of x equal w. So that's per x, and in particular, Kp of w, which is the largest solution to this equation, right? It's just the maximum, the largest x for which this holds by definition, and because of that, it's exactly the maximum root of this polynomial, right? So given p and w, we can actually express Kp of w as the max root of some other polynomial. What polynomial? Well, it of course depends on p and w, and it's this polynomial. It's you apply the operator u with a corresponding parameter alpha, which is 1 over wd, to p. Okay. So, couple of remarks. So, first remark is that I kind of wrote something here, which is not completely obvious. So I wrote the max root of a polynomial. Now, whenever some stranger in the street comes and tells you the max root of a polynomial, you should be sure that this polynomial is real-rooted, because otherwise it makes no sense. And indeed, what you can show is that if you start with a real-rooted polynomial, then this operator also produces a real-rooted polynomial. It's not trivial, but it's not so hard. I mean, you should, when you try to prove that, and I'll leave that to you. You should just remember that the derivative of a real-rooted polynomial is real-rooted, right? Because the roots kind of interlace the roots of the original polynomial, and are exactly the right number of them. If it was d, it's now d minus 1, so then all roots are real. And u alpha of p is really essentially that, right? It's p minus alpha times the derivative, so it's kind of the same, more or less the same argument. So I'm going to just leave it to you if you want to prove that if p is real-rooted, then also u alpha p. If you want a proof, it actually appears in a paper with Gal Maor, our TA, and Itai Cohen. I'm sure it appears in other places as well, but that's one reference I know of because we wrote it just for completeness. And then you can see it. It's search something about the zigzag product and with us free offers, and you'll find it. But it's not so hard. It's kind of annoying because sometimes you have multiple roots and then you have to be a little bit more careful, but it's all the same. Now, what's less obvious, and that's a theorem, not just a lemma, is that also, and actually we kind of, we didn't talk about it, but we should have already in the definition. When we define the additive convolution, we define it right as the additive convolution of two characteristic polynomials as the expected characteristic polynomial with respect to some orthogonal symmetrics. Not say I really care about orthogonal matrices now, because I mean we knew that this is real-rooted and this is real-rooted, but who told you that this is real-rooted? Right? I mean, it's not generally the case that the sum of two real-rooted polynomials is real-rooted. Sum or average, it's all the same, but the additive free convolution actually, or other operators other than sum, but the additive free convolution is real-rooted given that the two kind of summands are real-rooted. And that's a theorem that we're going to prove ahead. So it will take some time to prove that, but just keep that in mind. I probably should have said that. before. It's a remark that I kind of remembered that I should have said that when I remembered it, I should have said that, okay? Okay, and here is a picture of that if you want to see it. So for example, if you take this polynomial, just some arbitrary polynomial, and you look at its Cauchy transform, so that's the blue kind of diagram that you see here, right? 4 is here, it's the last pole, it's the rightmost pole because the largest root is of this polynomial is 4. Then you have all of these things in between, the usual picture that we have. So that's the Cauchy transform. And I chose some W, which is say 1.2, just for example. So that's the kind of purple line here, purple horizontal line. And I drew this polynomial. So the operator U alpha, with alpha being 1 over dw, d is 4. So 1 over 4w, evaluated that or applied to P. So that's the green thing that you see. These are not poles, by the way, just you see there are some angles to them, just like very vertical, like branches like that. It's a polynomial, it's not a Cauchy transform. It doesn't have poles, but you can see that indeed the largest root of this polynomial is kind of precisely where it should be. It's where the last, it's the max inverse of the Cauchy transform when W is set to 1.2. Okay, just a visualization of that. Okay, so we are also going to use the R transform. So we defined the Cauchy transform the same way the K transform for polynomials was as the max inverse of the Cauchy transform. But as I remarked, it's the same thing. It's a different way of stating it, but it's the same K transform from before. So we're going to define the R transform also as analogous to that. So we're just going to subtract minus 1 over W. And that's the theorem that was key when we talked about free probability theory, right? Let's call it the R transform theorem. The key result in finite free probability is not as strong, but it's good enough for us. So let's call it the FFP R transform theorem or the finite R transform theorem or R theorem or whatever. I actually didn't see a good name for it like in the paper, so I'm taking the freedom to invent any name I want for the purpose of the course. So what the theorem tells us, it tells us that for any W larger than 0, that you should think of it as this vertical line, that as it goes up, you get closer to the max root. And for any real-rooted polynomials, RRP, so real-rooted polynomials, P and Q, and let's take those to have degree exactly D, and with positive leading coefficients. So the Cauchy transform will look like we like it and not reversed. Okay, then the thing that you can say is that the R transform of this polynomial, the additive convoluted P and Q, at any W larger than 0 is always smaller or equal, not equal here, but smaller or equal, that's good enough for us, than the sum of the corresponding R transforms. So you should look at this. Okay? And actually, I mean, that's actually interesting because inequality is good enough. Equality, in a sense, is kind of a weaker, of course, it's a stronger statement, but it's a weaker statement in the sense that we would prefer for the purpose of bounding the support for this to be a strict inequality, actually, because it will give us a better bound on the support. So what happens in a sense, and I'm sure that you can make it formal, and maybe someone already did and I'm not aware of that, is that you can think of this as the kind of limit behavior of that. So this thing can actually be inequality. In fact, part of the theorem tells you that equality holds only if one of these polynomials at least is constant in a sense. It has only one root. So it's of this form. All right, so the corresponding measure is a constant on lambda. So usually, in a sense, you have inequality, not equality, which is good for bounding the support, because we will see, but it's not there yet. But the better the bound, the better is the bound on the support. The better the bound on the R transform, the better is the bound on the support. And in free probability, like infinite free probability theory, you have equality. So in a sense, the inequality is kind of irregularity that happens only in finite dimensional things. And as the limit goes to infinity, you cannot expect getting inequality. You should get an equality. So in a sense, it's actually a stronger theorem. It tells you more. It also tells you less, because equality is a way of getting the entire information about the measure. Inequality will only bound the support, but a better inequality, like strong inequality, is a better bound on the support. So it's kind of incomparable to remarkable theorems, and at any rate, that's what we are going to prove. Now, the proof is going to be by induction on the degree of the polynomial or polynomials, the largest one. Here we took them to be the same degree D, but we are going to refine it later. And we are going to need a way to kind of move to do the induction, to go to like a lower degree, something. So the technical tool that will allow us to do that is called the pinching lemma. You will see why, it's a good name. And the lemma is kind of a mouthful. It takes some time to state. So we are going to end this part of the lecture by stating the lemma, and then in a separate lecture or video, where it's the same lecture 10, sorry, but in a separate video, we are going to prove the lemma. Okay, the proof is kind of, it's one of these things that you can actually skip with not hurting too much your understanding. And anyhow, I think this video is long enough. So let's look at the statement of the lemma. You see, it's kind of long, and it actually continues on in the next page. But before that, let's actually define the polynomials that we care about. So for a number D larger or equal than 1, we denote by P, this cool P with a double leg P of D, is the set of all real-rooted polynomials with degree exactly D. Okay, we're going to care about the exact degree of the polynomial rather than at most D. And we are going to assume they have positive leading coefficients. We don't care about being monic, but positive leading coefficients. So these are the polynomials that we are going to work with now. And what does the lemma tells us? It tells us that if you have such a polynomial, and let's assume it has at least two distinct roots. The single root case, like x minus lambda 2d, is going to be simple. So let's assume it has, it's not going to require induction. So let's assume it has at least two distinct roots. Okay, and also let's assume P is monic just for the lemma's sake. Okay. So the definition of PD requires only positive leading coefficient, but let's assume for simplicity it's monic. So of course you can write the polynomial like that because it's real-rooted. It has the roots. The lambda i's may repeat, but let's write it like that. And as usual, lambda 1 is going to be the largest root, lambda d is the smallest root, and equality can occur. But because we are going to assume that we have two distinct roots at least, then there is some k. I don't think you should take the minimal k, but let's take the minimal k. There is some k which is smaller than lambda 1. So let's denote by k the first index, which you don't get lambda 1 anymore. Okay. Then for every alpha that you're going to give me, every alpha larger than 0 that you're going to give me, I can find two numbers, mu and rho, two real numbers. And I can, with these numbers, using these, I can decompose the polynomial in the sense that as a sum. I can write the polynomial as a sum of two other polynomials. In a sense, each of them is going to be simpler than the original polynomial. So we're going to have P tilde and P hat. P tilde is going to be that thing. So P tilde is going to have a double root at mu, right? So for every alpha, I promised you mu and rho. Okay. So the mu is going to be this extra root that P tilde is going to have. And we say it's pinched because it's double root, right? So we pinched lambda 1, lambda k to mu in a sense. And the other roots are the roots of p. So excluding lambda 1, lambda k, we have all other roots. I mean, if lambda 1 appears more times, it will appear also here, but just one time less. Same for lambda k. So this is a polynomial with a double root, a pinched root, and it's also note it's a degree d polynomial. It's monic, it's reed-rooted, so in particular it's in PD, right? We don't even need the monic to be in PD, but it's monic. So, right, so you wrote P as P tilde, which is kind of a pinched polynomial, plus P hat. And what's P hat? So P hat is also going to be simpler. In a sense, it's going to be simpler in a simpler way. It's going to be of degree d minus 1, okay? So P tilde was not a degree d minus 1 polynomial. You cannot expect, of course, to write a degree d polynomial as the sum of two degree d minus 1 polynomials, but the degree d part is in P tilde, and P hat is, again, like P tilde, it has all the roots that P has, but you remove one instance of lambda 1 and one instance of lambda k, and you replace it with this new root rho, right? So again, for every alpha, I promised you a mu and a rho. So mu is going to be the new kind of pinched root of P tilde, and rho is going to be the new root of P hat. I'm going to say what we know about them in a second, but some bounds about them, but that's that. And actually, this polynomial is not going to be monic. It's going to have this as the coefficient of x to the d minus 1. And actually, that doesn't appear in the original paper. So there is a little typo in the original paper, which kind of forgot to say that. But, whatever, it's there. And one thing that we should say is that this is indeed positive, right? Because if it's negative, and technically this polynomial is not in PD minus 1, because PD minus 1 are positive leading coefficients, so this is indeed positive, we will see that. Namely, we will see that 2 mu minus lambda 1 plus lambda k is larger than 0. Okay? So to recap, you can write any polynomial in PD, let's say it's monic, as a sum of two polynomials which are simpler. More precisely, for any parameter alpha, you can find the two polynomials. The tilde one will have the same degree, so it's not going to be simpler in that sense, but it's going to have a double root. So in a sense, the number of these distinct roots goes down by 1. And P tilde is going to be a degree d minus 1 polynomial, so it's in a simpler way, a simpler polynomial. But what do we know about this mu and rho? We will need to know some stuff then, or about more generally about P tilde and P hat. So first of all, the max roots, right? The max root of U alpha P is something that we care about, because that's related to the K transform, right? So the max root is going to be the same for all. So with the same operator U sub alpha for the alpha that you gave me, the max root of U alpha P is the same as the max root of U alpha P hat and a max root of U alpha P tilde. And from here on, we are going to just abbreviate this as MR when we write max root. Mu is going to be between lambda 1 and lambda k. So, right, so this new pinched root is not going to be larger than lambda k. It's going to be kind of between lambda 1 and lambda k. And so therefore, you kind of expect maybe that rho is going to be larger than lambda 1. And that's true, right? Because if you have these two and you kind of pinch it, then some kind of conservation of mass or whatever should make sure that there is something that pull it to the right. So the rho, the max root of P hat is going, it is the max root of P hat because rho is larger than lambda 1. It's going to be larger than lambda 1. And in particular, know that if you started with a degree at least 3 polynomial, namely if P was a degree at least 3 polynomials, then P hat is going to have at least 2 distinct roots, because rho is larger than lambda 1, so it doesn't appear here. And there is at least one more root here, which may be lambda 1, but rho is larger than lambda 1, it's larger than all roots. because you only excluded two roots, and if the degree is 3, you started with 3 roots, right? So you have at least 2 roots. Okay, so as I said, the proof of this lemma, you saw it's like a kind of a technical lemma. So the proof is also, it's actually less mouthful than the statement. But it's technical, and you should feel comfortable just, looking at it in a second pass, or not at all. It really has nothing to do with free probability or finite free probability, just a little lemma about polynomials. But maybe you can say that on everything that we are going to do from here on, so I'm not sure that's a good reason. But anyhow, we are going to stop this video here, and the proof of this lemma is going to appear in the next video. And after we are going to do that, we're going to go back to, it's kind of long, to prove some other preliminary results for, we're going to continue the proof, but proving some preliminary other lemmas for the R theorem for finite free probability.